Okay, so today we're going to take a look at the 6.5 material working with dividing monomials. Now we'll make a very clear distinction here when we are dividing monomials versus dividing polynomials. We're working with a very, very specific instance here. But we can and will see the expanded version of this or the more generalized version of this in later sections, I believe primarily in Math 97, the next class after this. So for the instances of this section, what we'll be seeing on the homework, we are working specifically with monomials. And we can think of the entire idea of dividing monomials as really just reducing fractions that contain monomials. That's the big overarching idea. If we need something to kind of simplify this down to, is we're just reducing fractions. We're just going to have some variables thrown in there now. So all of our previously used, previously learned properties with exponents are still going to apply here. So our product rule, our power rule, and our product to a power rule, and all of our previous rules for establishing and determining what is and is not the base of an exponent, we're still going to apply that here. But our new properties that we're going to be using, specifically for dividing monomials, are the quotient property, the zero exponent definition, and the quotient to a power property, which we'll go through here now. So the quotient property says that for a non-zero value of a, so a can be anything that isn't zero, if I have a to the m divided by a to the n, then I have one of two scenarios that are going to show up. If the m exponent, or value that we have up here, is greater than our n value, the exponent down below, then the answer to this is going to be a to the m minus n power. And you would subtract those two numbers and you'd have an answer. If it ends up being the reverse of that, if m, variable up here, or exponent up here, I should say, if the exponent m is less than the exponent n, then a to the m divided by a to the n is going to have the result of, we'll have our answer right down here, it's going to be 1 over a to the n minus m. So we have two ways of working through this, two ways we can write this out, and we're actually going to get a really nice generalized version of this where we will use just the first one once we've gone through negative exponents. Negative exponents are something that we're going to be covering in the 6.7 material. So this is the specific one that you want to know. The exponents will subtract top minus the bottom. And then if you are not comfortable with working with negative exponents yet, you could use one of these two as your answer. If you are comfortable with negative exponents, then you'll know what to do with that. But we will get to that in our next section. We also have the zero exponent definition. And the zero exponent definition tells us that a to the zero power is always equal to 1, as long as our a value, meaning the base of the exponent, is not 0. It's a very, very, very strict rule there. So anything to the 0, except for anything to the 0th power is going to equal 1, as long as that anything is not a 0. 0 to the 0 power is undefined. We do not know the answer to that. And I'll go through the reason why we don't know that here after we're done with this and we get into some of the examples. But this is a very commonly made mistake. Anything to the 0 is just 1. Well, except for 0 to the 0, which is undefined. It's the only exception to that. But as long as you have a non-zero base raised to the 0 power, your answer will always be 1. It could be a really nice number, like 2 or 10 or -3. It could be a decimal, it could be a fraction, it could be a really big number, a really gross number, a mixed number, who cares? As long as it is a non-zero number and is raised to the 0 power, our answer is going to be 1. And we'll see how this works out actually in a couple example problems down below here. And last but not least is our quotient to a power rule. So a over b, all raised to the m power. It's equivalent to saying a to the m divided by b to the m. And we're assuming b is a non-zero number, so we do not create division by 0 in our denominator spot. It's very similar to our product to a power rule, at least with how we work with that, except here, just instead of a product, we have a quotient being raised to a power. Now, just like we did with all of our previous properties, we have these new ones showing in. We can use these and kind of have multiple strategies for going about solving and simplifying some of the problems that we're going to see. And we can go about doing these in a couple different ways, a couple different processes for them. There's always the option, and I'll show a few examples of this, of expanding what we're working with and then canceling things out to see what our final answer is going to be. It's generally the one that shows up with the quotient property. And you're fine with doing that, but we're going to see with some of these numbers, we're going to get a lot of things showing up, and it would be, it's going to be a waste of time to write something out that many, a variable or a number out that many times, as we'll see coming up here shortly. So when we are also working with these, we're using all of our properties, but remember, if you are told to simplify, PEMDAS, that order of operations guide, governs our process for simplifying expressions. That means all of our previously established rules for fractions, as well, for addition, subtraction, multiplication, and division, still hold true even if the numerator and denominator contain variables. So we still add, subtract, multiply, and divide a general fraction the exact same way. Now we just have a couple different ways that we can work with it if we have exponents and variables showing up in there. I'd also like to remind everyone that when we are working with fractions, a common denominator is required only for when we're doing addition and subtraction with fractions. You do not need a common denominator for multiplication or division with fractions. Okay. So from here, try and go through quite a few of these examples if possible, just to see how we can and will be working with our new properties that we have showing up here. So I'm going to jump us over to the Blackboard, but these are the examples that we are going to go through. And we're actually going to see the zero product or zero exponent definition show up here in a little bit. But I'm going to go through these examples that we have here first. So we'll jump us over there. Let's get started on them. So our first example that we have, and again, with all of these, we are told to simplify. So if you're wondering, okay, how can I go about simplifying this thing? What should my first step be? What should I do next? Remember, if you see the word simplify, you should immediately think to PEMDAS. Parentheses, exponents, multiplication, division, addition, subtraction. That is what's going to govern how we go through these problems. So our first example that we have is x to the 43rd power over x to the 38th power. Now again, if you wanted to, I wouldn't recommend this, but you can go through and you can absolutely write this thing out as x times x times x times x 43 times in the numerator, and then x times x times x times x 38 times in the denominator, and then cancel things out. You are welcome to do that. I would not recommend that because that's going to take a very long time. So instead, we're going to apply the quotient property that we just learned. And our quotient property says that if I have something raised to a power divided by that same thing, same base, raised to a power, I can subtract the exponents together. So if the bases are the same and they are dividing, the exponents subtract. So what this looks like, 43rd, is really I'm getting x to the 43rd minus 38th power. So 43 minus 38, that's going to give me 5. When we get to some of these larger, more extravagant numbers, you are, again, more than welcome to use your calculator to do the number crunching for yourself. So when we fully simplify this thing down, again, using our our quotient rule for this, if the bases are the same and they are dividing, the exponents subtract from one another. And now we're going to see with our second example how that works and how we can look at it. I'll show this one with the property and an expanded form so we can see where this pans out. So our second example that we have is n to the 3rd divided by n to the 7th. So go about this. I'll show you multiple ways of how we can see this and think on this thing. So the bases are the same and they are dividing, which means the exponents are going to subtract from one another. Now, if we are not comfortable with using our main method of using the quotient property and we get negative exponents, if we're not comfortable with that, that's fine. Written into our notes, as it's written in there, if m is greater than n, which means if m is less than n, my mistake, if the numerator exponent is less than the denominator exponent, then what I'm going to get is I'm going to subtract these two, but I'm going to write them in as the larger minus the smaller in the denominator of a new fraction. And I'll go through and show an expanded form of this as well to illustrate why this is. But then we would just do the subtraction, and we would get 1 over n to the 4th power. So we have our answer there. Now, if we were to go through, and a lot of people have this question come up, well, how do we know and why does it arbitrarily go in the denominator spot? So here's the alternate version that you can always do with these. It's kind of the nuclear one, but I would not recommend doing this too often, only because numbers get big and gross sometimes when we're doing this. So let's say we wrote this thing out in expanded form. So in the numerator, I have a base of n, so I have n times n times n. In the denominator spot, I have n times itself 7 times. Okay, so we have it written out here. Now again, we have a fraction we're working with, so if I have something in the denominator or in the numerator and the exact same thing in the denominator, I can cancel those out. So I can cancel out these n's, and these n's. In the numerator, I'm just left with 1 remaining. Each of these things will become 1s. So 1 times 1 times 1 is just going to give me 1. And in the denominator spot, I have four n's multiplying together, which is the same as saying n to the 4th power. The exact same answer that we just got, but written out in a slightly different format. So another way you could go through and write this out. Now, I'll give you guys a little bit of a preview of working with negative exponents, but we're going to go through these in a lot more detail in the next section. So if we have n to the 3rd over n to the 7th, and let's say you don't want to use the specific property that we have listed for the quotient property in our notes right here. You just want to do the numerator's exponent minus the denominator's exponent, which is perfectly viable. Nothing wrong with that. Let's write it out for ourselves. N to the 3rd minus 7, n to the 3 minus 7 power. When I subtract those together, I get n to the negative 4th power. And then the way we deal with negatives is we correctly identify the base and we flip that fraction. So technically, the base of this is n over 1. Remember that invisible 1 that hangs out there. So all a negative exponent does is say this thing goes from whatever part of the fraction it's in to the opposite part of that. So our n is technically over 1. It's in the numerator spot. The negative exponent up here says I'm going to take this base, n, and instead of having it in the numerator spot, I'm going to put it into the denominator spot. The numerator is just going to become 1. So I got 1 over n to the 4th. Exact same thing as we had before. So again, this is the if you are already comfortable with using negative exponents method, great. If you aren't, that's fine. We're going to get to this in our next chapter, or next section, I should say. But 3 different ways you could go through and solve this thing out for yourself. I am perfectly happy with whichever one you would like to use on the homework, whichever one you would like to use on the test. It is your call. So moving on to our third example that we have here, we have y to the 11th divided by y to the 11th. So again, we have a monomial divided by a monomial. And based on that, what I can do is I can say the bases are the same. They're both y's, and they are both dividing. So I can take the base and I can subtract the exponents. We have y to the 11 minus 11th power. That gives me y to the 0. I believe we're assuming that all the bases are non-zero numbers, which means that anything to the 0 power is just going to be 1. Now again, we can think on this. I'll write part of this out in expanded form here. Why are we getting this thing just canceling out automatically to being 1? Very reasonable question to ask. Let's figure out why. I'm showing an alternate method. So I have y to the 11th over y to the 11th. I'm only going to do this once because there's a bunch of writing that goes into this. But if I have so I have 11 y's up top. I think I do. 1, 2, 7, 8, 9, 10, 11. Yep. So I have 11 y's up top. Oops. Raise that there, make it a little bit better. Okay, 1, 2, 3, 4, 8, 9, 10, 11. Okay, 11 y's down below. Now, we have it written out in expanded form, which means that whenever I have one thing in the numerator and the exact same thing in the denominator, I can cancel these out. So each of these cancels, which means each of these things would become 1s. 1 times itself 11 times is just going to be 1. 1 times itself 11 times in the denominator is just going to be 1. 1 divided by 1 is just going to be 1. So we got our answer here. Now, the reason that we always need to have a non-zero base if we have something raised to the 0 power comes from the fact that we don't actually know what 0 to the 0 power is going to equal. There's a couple reasons for that. So why is 0 to the 0 power undefined? So why this is, there's two different trains of thought with this, with which there are two trains of thought, and both of them lead to to the conclusion that we would reasonably assume, but this is where we get the weird part showing up. So let's think on this. Let's think if we had 0 to a power. So let's say we had 0 to the 3rd power. Well, 0 times itself 3 times is going to be just 0. 0 to the 2nd power, same idea. 0 to the 1st power, be that. And let's say 0 to the 0 power would also be 0, following this train of thought, which absolutely makes sense. So at the very bottom, we see 0 to the 0 power equaling 0. And following this train of thought, there's nothing wrong with that. Pretty logical and it makes sense. So let's say we're working with, we'll say 2 to the 2nd power, or 2 to the 3rd power. Stay consistent here. So 2 to the 3rd power is going to give me 8. 2 to the 2nd power is going to give me 4. 2 to the 1st power is going to give me 1. And then 2 to the 0 power, as we just saw previously, or 2 to the 2nd power is going to give me 2. Sorry. 2 to the 1st power, or 0 power, is going to give me 1, as we just saw with our previous example. Something to the 0 power giving us 1, especially if things cancel out. Now, the interesting part that goes along with this is, okay, well, I've got something to the 0 power, or where am I at here? It stands to reason, based on this, excuse me. Well, how come then, how are we getting that one of these things, which makes complete perfect sense, is going to equal 1? And how come then with the same instance it's going to stay equal to 0? So if we treat 0 like it's a number, like we would with 2 or 1 or anything like that, why then, following our train of thought, a number to the 0 power would give us an actual number, which 0, being a number to the 0th power, should also reasonably be 1 as well. But if we also define 0 to be nothing, nothing raised to the 0 power should also remain as nothing. So following these two trains of thought, we get the thought of, well, 0 to the 0 power equaling 0, or 0 to the 0 power equaling 1. Treating 0 as nothing, or treating 0 as a number value. This is where the tricky part comes in and why we don't know which answer it's going to be. Which is why we have 0 to the 0 power listed as undefined. And if you're sitting there thinking, okay, well, each of these respectively makes sense, but the whole rationale as to why it would be one time it would be a 0, some other time it would be a 1 doesn't make sense to me. And if that's why you're confused, that is 100% why 0 to the 0 power is undefined, because we don't know its value. Because of that tricky, it could be one, it could be the other kind of mentality to it. So we've simplified it as mathematicians and just said it's undefined. We don't know which one it is. So that's how we are getting the main part of 0 to the 0 power. It's an undefined answer. So I'm going to go through a couple more of these examples. So if we have, let's say, example 4, this is working with 5 to the 7th power, all to the 3rd power. So here we have a quotient to a power. So writing this out, using our quotient to a power rule, that tells me that the numerator is going to be raised to that power, divided by the denominator raised to that power. Now apply your calculator. 5 to the 3rd power, that's going to be 125. Then 7 to the 3rd power, I'm doing that off screen here. Just using a calculator, 7 to the 3rd power is going to give me 343. And again, if you do not want to use this method, you can alternatively, you can write this out in expanded form. 5 over 7 times 5 over 7 times 5 over 7. The base of the exponent, which is everything inside the parentheses, multiplied by itself 3 times. So you get 5 to the 3rd, which is 125, over 7 to the 3rd, which is 343. And you get the same answer either way. So again, these properties are meant to be shortcuts for us. Save us some time as we're going through and working on these problems. So I'm going to move us over here. We're going to take a look at, oops, there we go, some of our other examples. So these are going to be a bit more of the in-depth ones that we have. This is where we have multiple steps as we're going through these things. So looking at example 5, we're working with quantity m to the 5th raised to the 4th, all over m, not n, m to the 7th. Now at this point in time, the knee-jerk reaction is, well, I have something being divided, so I have to use the quotient property here. And the knee-jerk reaction to doing that is not an unreasonable one. However, it is not going to be our correct first step that we're going to take here. We need to follow PEMDAS because there are more things that are going on than just division. So following PEMDAS, because again, we're told to simplify this thing. Inside the parentheses, can I do anything to that m to the 5th power? No, I can't. So parentheses, done. Exponents, can I apply any exponents to anything? Well, I have m to the 5th. Okay, well, I can't do anything with that. I have m to the 7th. I can't do anything with that. And then I have everything inside this set of parentheses being raised to the 4th power. which means I have an exponent raised to an exponent's power, using the power rule here. So m to the fifth, all raised to the fourth power, tells me that my exponents are going to multiply together. So I get m to the fifth times fourth, or m to the 5 times 4 power, which gives me in the numerator spot m to the 20th over m to the 7th. So I've just applied exponents. I can't do anything else with them now. Multiplication or division, I have m to the 20th divided by m to the 7th. Using our quotient property, we get the bases are the same. They are dividing, so the exponents will subtract. We are getting m to the 13th as our final answer. Let's make this a better 13 here. There we go. And then we have our final answer. Let's take a look at, I'm going to jump us ahead to number 7. That's got a lot more that's going on with it. And again, as you're going through these, and if you're saying, I don't really know where to start with these, if I've got a bunch of stuff going on, again, if you're told to simplify, look to PEMDAS. It gives you your step-by-step guide on what to do with these things. So for number 7, we have a to the second power all to the third times a to the second, all raised to the fourth power. And the denominator is a to the fourth raised to the fifth. So there's a lot going on here. But we are going to let PEMDAS help us out with this. So first and foremost, parentheses. Can I do anything inside the set of parentheses that I have showing up here? I have a to the second, and a to the fourth. So I know I cannot do anything inside the set of parentheses. So that's fine. Moving on to exponents. Can I apply any exponents in here? Well, I have a to the second all raised to the third power. I have a to the second all raised to the fourth power. And then I have a to the fourth power all raised to the fifth power. So I have 3 exponents that I can apply here. And I'm going to be applying the power rule to these. A to the second raised to the third power. That's going to give me a to the 6th. Still multiplying. A to the second times, or a to the second raised to the fourth power is going to be a to the 8th. Again, the exponents multiply. And for our denominator, a to the fourth power raised to the fifth power is going to give me a to the 20th. So here I've just applied the exponent properties. And now I'm working with multiplication and division. In the numerator spot, I have a to the 6th times a to the 8th. That's going to give me a to the 14th over a to the 20th. Now I have division going on. I have a to the 14th divided by a to the 20th. Using our quotient property. It's the same as saying a to the 14 minus 20th power, which gives us a to the negative 6th. And then you would need to rewrite that into being a fraction of a, or 1 over a to the 6th power. And again, I'm using this negative exponent one, or version of solving this thing out, which we will be getting to in 6.7. Partially out of habit, but partially out of, I think it's a bit easier to work with than having to keep track of some of the other stuff that goes along with how many are in this spot, how many are in another spot, that shows up. But again, you're welcome to use either of our previous methods for using the quotient rule to get through this thing. So this is number 7. And we'll round it out with question 8, and we'll end our recording there. Extend our dividers here so we keep our work separate from itself. So question 8. We've got a lot going on here with this one. Bye. Okay. So we've got this going on here. We have the quantity negative 12 x to the 6th y to the 9th times the quantity negative 4 x to the 5th y to the 8th, all divided by negative 12 x to the 10th y to the 12th. And again, if you do not know where to start going through this thing, that's fine. Look to PEMDAS as your guide. Can I do anything inside the sets of parentheses? No, I cannot. I cannot simplify those down any further than where they are. So parentheses, done. Do I have any exponents that I can do anything with? Well, I do have exponents, x to the 6th, y to the 9th, x to the 5th, y to the 8th, x to the 10th, y to the 12th showing up in here. Great, but I cannot do anything with those right now. So nothing is being raised to a power that I can simplify. That's fine. Multiplication or division, I have both of those going on. Let's work with simplifying the numerator first, and then we'll deal with dividing this fraction out. So in the numerator only, working with numbers, x's, then y's. Numbers, I have negative 12 times negative 4. So you get positive 48. I have x to the 6th times x to the 5th. The bases are the same and they are multiplying, which means the exponents add together, and I get x to the 11th. I have y to the 9th times y to the 8th. The bases are the same and they are multiplying, which gives me y to the 17th. So exponents add together. It's our product rule. And the denominator remains as negative 12 x to the 10th y to the 12th. So looking at our PEMDAS tier list, I did multiplication. Now I need to do division. So again, numbers, x's, then y's. 48 divided by negative 12, that's going to give me negative 4. X to the 11th divided by x to the 10th. The bases are the same and they are dividing, which means the exponents will subtract. So 11 minus 10, it's going to give me just x to the first power, or x. And then y to the 17th divided by y to the 12th. The bases are the same and they are dividing, which means the exponents subtract. So I'm going to get y to the 17 minus 12 is going to give me 5. So y to the 5th. I can't do any other simplification with multiplication division. I have no addition subtraction, so I am now done with this problem. It's fully simplified. And this is using our properties for dividing monomials together. Again, the methods, the properties and all that is specific to having a monomial divided by a monomial. Nothing says we can't have monomials multiplying together, so we simplify it down and then get to a final answer, but this will only work for monomials. If you have a binomial, trinomial, anything like that showing up, none of these properties will work. Or at the very least, we have to work with them very differently. Okay. So this is everything that we have for the 6.5 material. We'll be ending the recording here. And yeah.